All right, welcome to Unit 1, Exploring One Variable Data for AP Statistics. This video is over topic 1.7, Summary Statistics for a Quantitative Variable. So everything we discuss in this video is for quantitative variables only. All right, so what is a summary statistic? Well, this is really important to start off with. A statistic is a numerical summary of sample data. It is a number that describes your sample data in some way. So keep in mind, a statistic is any numerical summary from a sample. So easy to remember. Statistics come from samples. S for statistics, S for samples. Hard to mess that up. So a statistic is, again, any number that represents your data in some way. Here's a couple examples that you might have heard of and maybe you haven't. The min, that is one value that is the lowest of all the data. That is a statistic. Why? Because it's a number that came from a sample. The max, that's a sample, or that's a statistic from a sample. The median, the mean, the range, standard deviation, Sarah's value. Now you might be like, Sarah's value? What I mean by that is any one particular value is a statistic. Why? Because it comes from the sample data and it somehow represents or describes that data. So you'd say, oh, Sarah got a 56. That's Sarah's score. That's a statistic. Also, a percentage above a value or a percentage below a value. So if you say something like, wow, I looked at all that data and 35% of data was above a 90. Well, that's a statistic, right? It's a number, 35%, and it describes your data. So all of these are statistics. So, keep in mind, if it's a number and it came somehow from your sample, it's probably a statistic. All right, so now let's talk about a couple famous statistics that are used quite often and all the time in this class. So the first, we have measures of center in position. These are values that somehow attempt to describe the center of your data or a position in your data. The two most famous measures of center are the mean and median. First, the mean. The mean is the sum of all the data values divided by the number of values. Pretty sure you've probably heard that before. All right, now the symbol we use is X bar. It is literally an X with a bar over top of it. There it is right there, and it's pronounced X bar. Now, this formula may really look foreign to you, but this is exactly what I said already. This giant looking E here stands for sigma, but anyway, that is the summation. So we're summing up all of our individual values. Xi just stands for the individual values. So you're going to add all those individual values up all the way from the first value to the nth value. So let's just say you have 45 values. You're going to add all of your values up. You're going to start with the first value and you're going to add all the way up to the 45th value. And then you're going to divide by 45. And that is where we multiply by 1 over n. Hopefully you remember that multiplying by 1 over n is the same thing as dividing by n. Duh, right? Easy. All right, so this is just a really fancy way of showing the formula. I don't really require that you remember it. I just require that you understand, add all your data values up and divide by how many values you have. Now, some facts about the mean. It's important to understand that they are easily impacted by outliers, as we discussed in class. If one upper outlier, the mean will go up. If one lower outlier, the mean will go up. So we did that example in class about home prices. If you have a bunch of home prices priced around $200,000 and then one of them is at $1 million, well then the average of the mean home price is going to move up a little bit because of that one really high value. Keep in mind, this is all because the mean takes every value into the data set into account. Every value is needed to calculate the mean. Now with skewed data, it will move towards the tail. And we did talk about this as well when we talked about shape. So when you have data that is skewed to the right, for example, so you have a bunch of data over here and then the data slowly trickles off to the right. Now, there are very few data values up here, but because of these super high values, then the mean is going to move up a little bit. Now, it's not going to come flying way over here, but it is going to move up a little bit. Now, there are lots of values down here that are going to, also impact the mean, but these values up here, even though there's a few of them, they will impact the mean as well. So when you're skewed right, the mean will tend to move a little bit to the right. When you're skewed left, the mean will move a little bit to the left. Now with symmetric data, the mean's going to stay pretty much right smack dab in the middle because the data is on the left side and the data on the right side will balance out and the mean will be right in the middle. All right, the median. The median of a set of data is the middle value when the data is ordered. So when you put all the data in order, the median is the dead center of that data. Now, when you have an odd number of data points or an odd number of values, there is always going to be an exact middle. For example, with 5 values, the third is the exact middle. 1, 2 below it, 4, 5 above it. But when your data values are even, when you have an even amount of data, what you're going to happen is, if you have 10 values, you're going to have 5 at the bottom, 5 at the top. So the median is actually the average of the middle two. So it's the average of those middle two values. Now, there is no formula to find the actual median, but what we do have is a formula to find the position of the median. So as long as your data is all in order, you could use this formula, n plus 1 divided by 2. So if you take how many values you have, so let's say I had 10 values, add 1 and divide by 2. This will tell you that the median, and 10 plus 1 divided by 2 would be 5.5. This tells you that the median value is not 5.5. Please don't think that. It tells you that it's simply located at the 5.5 value, which means right between the 5th and the 6th value, as long as they're in order, is where the median will fall. If you have an odd amount of data, like say you have 7 pieces of data, plus 1 divided by 2, that's going to be 4. That means the median is the 4th value. 1, 2, 3 above it, 5, 6, 7. 1, 2, 3 below it, 5, 6, 7 above it. So the median is the actual 4th value. But please, I can't stress this enough, this formula does not find the median, it just tells you where to go and look for it. So what are some facts about the median? First, it is not impacted by outliers. Remember, the formula actually doesn't take the values into account. There is no formula to find median. You guys got to go find it. It's the dead middle. So the actual values themselves don't impact the median at all. It's always going to be smack dab in the center. So if there is a $1 million house in your data, then it doesn't matter. The median doesn't care what the value is. It just wants to go to the dead center of all your data values. So keep in mind that 50% are above it, 50% are below it. And it's also known as the second quartile. Think of second quarters, 2 quarters. 2 quarters are worth 50% or 50 cents, right? So 50% below, 50% above. All right, now we have a measure of position. Now this is a very famous vocab word that we'll use a lot this year, but it's percentile. The p percentile of a set of data is interpreted as the value that has p% of data less than or equal to it. For example, the median is known as the 50th percentile because it has 50% of data at or below it. So keep in mind when we see these percentiles all the time. For example, if you get your ACT score, you might read in your score report that you were at the 85th percentile. What that means is that 85% of students scored at or below your score. It also means that 15% scored better than you. So even though the definition of a percentile is at or below, you can do some quick mental math to figure out the above. But the official definition of a percentile is the percent of data less than or equal to it. So it's really easy to find a data values percentile. All you have to do is count how many values are at or below that value of interest, then divide by the total number of values. So if you got a 72 on a test and you want to figure out what your percentile is, all you got to do is count how many kids scored below you or at your 72 and divide by the total number of kids in the class, and you'll get your percentile. A percentile is a nice way because it's relative, right? It's a percentage. It tells you where you fit into the data. So if you got a 99th percentile on your ACT score, that tells you right away that you fell at the very, very, very top. 99% of kids did below you or at your value, and only 1% did better than you. So it's a nice way to kind of get a feel for where you fit in the data. All right, next up we have the quartiles. These are more measures of position, right? These tell you where a value is located. The first quartile is the median of the lower half of the data. So think of it as the middle of the bottom half of your data. So the median splits your data in half. Quartile 1 splits that bottom half in half. So this is the 25th percentile. So we're looking at that bottom 50% of data, splitting it in half, 25th percentile. The third quartile is the median of the upper half of your data from the median to the max. So if you look at the top 50% of your data, this would be between that. So this is known as the 75th percentile. So I kind of think of it like this, right? Remember, median, Q1, Q3, these don't care what your values are. So I just think of, here's my data, blah, min to blah, 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 max, right? The median falls right smack dab in the middle, 50% above, 50% below, also known as Q2. Here's Q1. It's the bottom, middle of the bottom half, hence the 25th percentile, because 25% is below it. But that also means that 25% is right here as well, because it splits that bottom in half. And then Q3 is right here, the third quartile, and that is known as the Q3. Well, I put Q3 there on top, right? This is known as the 75th percentile, Because again, if it's the middle of the upper half, then that means it takes the upper half and splits it into 25%, 25%. And then remember, the definition of a percentile is the percent below. So that's why we get 75%. You can literally see the 75% below Q3. So the quartiles are a nice way to break up your data, and it also allows you to see the middle of the data, because between the first and the third is the middle 50% of your data. And you can easily see that right here, right? So if I look between the first and the third quartile, that's my middle 50% of data. And again, like I said earlier, median, Q1, Q3, they don't take the values into account at all. They just want to locate the centers of the middle of the data, the top of the data, and the bottom of the data, and so forth. All right, next up, we have some more statistics. Remember, these are all statistics because they're all numbers that come from our sample data. Next up, we're going to talk about measures of variability. These are values that measure spread. Okay, so these are values that describe how a set of data varies or spreads. Now, sometimes this can confuse students because they're like, how can a number tell me that? Well, that's what I'm going to teach you right now. So think of it as a single number that tells you how much the data varies or doesn't vary. So now there are three of them we're going to learn about. First is range, which I'm sure you've already heard of. Number two is the interquartile range, which is probably new to you. And then the third is standard deviation, which you may have heard, but I bet you've never really understood. All right, so first off, range is pretty simple. It's simply the difference between the maximum value and the minimum value. So it's your max minus your min. Now, bigger range means that your data is more spread out. Duh. Smaller range means your data is less spread out. So that's how one number, the range, can tell you how your data is spread. However, the range is really easily influenced by outliers. Fix that typo there, sorry. The range is easily influenced by outliers. So one very large value in your data will cause the range to look very big. So imagine if you have a bunch of home prices again, and they're all around $200,000 to $300,000, and then there's one of them that's $1 million. Well, if you use that $1 million as the max, because it is, you calculate your range, it's going to look like you have this huge spread, but really it was just one value that was an outlier. So that's why, to be honest, we really don't use the range that often to talk about data. In fact, this might be the last time I ever mention it, because it's so easily affected by outliers. A much better value to use is known as the interquartile range, which we abbreviate IQR, interquartile range. This is the spread of the middle 50% of your data. It is defined as the difference between the third and first quartiles. So Q3 minus Q1. So it's kind of already mentioned this in that previous example where I showed you the data, right? And I just said, hey, it's the middle 50%. So between Q3 and Q1 is the middle 50% of your data. Now, why is this a better measuring tool for spread? Well, because it doesn't get impacted by outliers. So if you do have that $1 million house, well, remember, I don't care about the overall range. I just care about the range of the middle 50%. A smaller IQR means that your middle 50% of your data is not very, is unspread out and clustered together. A very large IQR means that your middle 50% is very, very spread out. So again, this is how one number, IQR, could really kind of tell you how your data is spread. So if your IQR is, only $1,000, well, man, that means that the middle 50% of your houses are very, very clustered together, all within $1,000. Whereas if your IQR is something like, an extreme of like $150,000, well, that means that that middle chunk of data, that 50% in the middle, is kind of really spread out in price. All right, last measure of variability here is standard deviation. The standard deviation is a great way to measure how spread your data is, and represents the typical distance a data value is from the mean. I underlined that because that is huge, because below this is the formula for standard deviation. And by the way, the symbol for standard deviation is just S, right? Or a lot of people might do S with a little sub X. It just means the standard deviation of your data. For example, if I'm measuring the heights of, elderly people, I might use S and then a little E here. So the standard deviation of elderly people. But, you don't really ignore that. Just use an S. It's fine with me. Now, keep in mind, this formula is really ugly, and it might not make a whole lot of sense to you. I'm going to go over how to actually do it in class, but I don't want you to memorize this formula at all. All I want you to understand is what it means, because we're going to use our calculators to find the standard deviation of data for us. But what I do want you to remember is what's in magenta there, pink maybe, is what the standard deviation represents. It represents the typical distance a data value is from the mean. So a small standard deviation tells you that most data, not all, is very close to the mean, hence unspread out, right? So if you have a very small standard deviation, it means that typically most data is very near the mean. Maybe a little bit above, maybe a little bit below, but it's near the mean. A large standard deviation tells you that most data, not all, but most data, is very far from the mean, hence very, very spread out. So if you have a large standard deviation, that means typically your lot of data, right, is really, really far from the mean. So I will say that most data is within one standard deviation of the mean, and understand that means up or down, right? So if let's just make up some numbers here. If I have a mean of 50 and I have a standard deviation of 2, well, that means that most data is within one standard deviation. So that would be 48 to 52. One standard deviation up, one standard deviation down. Because one standard deviation is 2. So 2 up, 2 down. So what this means is that a large chunk of data, not all, and I'm going to say that a lot, but most data is within 48 to 52. That's a pretty small spread. That's pretty much clustered real close to 50. But let's do a second example here up top here. Imagine if your mean was 50, but this time your standard deviation was 20. Now, I'm still going to go with what I already said because this is always true. Most data was within one standard deviation. So that would be down to 30 or up to 70, right? One standard deviation down would be 30. One standard deviation up would be 70 from the mean. And that is a very big spread. That means my data is going all the way from 30 all the way up to 70. That's a lot of data that's spread out. So that's how standard deviation connected with your mean really could tell you a lot about how your data spread. Now, keep in mind, I keep saying some data, but not all, right? Let's go down to this green example. Yes, the majority of data, most of data will be from 48 to 52. Does that mean there can't be a data value up here at 60? Sure, there still could be, but that wouldn't be where most data is. Most data would be in here, right? And I'm not going to give any kind of percentage or anything like that there. Just the idea that a large chunk of your data will be within one standard deviation of your mean. So the standard deviation is interesting because it really kind of tells you how much data you have and how it's spread out. All right, so who likes to go together here? So let's just start with what I just kind of ended with. The mean and standard deviation are always paired together when you talk about center and spread because the definition of standard deviation is how far typical data is from the mean. So they are partners in crime. Now, when do you use the mean and standard deviation to describe data? Anytime you're symmetric. If you're symmetric with no major outliers, use the mean and standard deviation. Remember, outliers and skewness will cause the mean to shift and not truly represent the data. So when we have major outliers and skewness, we don't like using the mean, which brings us to what's over here. The median and the IQR are used when you have data that is skewed or has major outliers. And the median and the IQR go together because it makes perfect sense, right? The median represents the 50th percentile, 50% above, 50% below. And then the IQR represents that middle 50% from Q1 to Q3. So they're all kind of hovering around each other there. That's why they really kind of go together. They represent the middle of your data. And when you have outliers, the middle of the data is not affected. That's why when we do have outliers and skewness, we like to go with the median and the IQR. Now, one last topic here to speak of, and that's outliers, since I've been mentioning a couple times. No more do I want outliers to be kind of your opinion. I want them to be official, right? So here's how we find outliers. We find what are called the fences. These are not actual values. These are just a process to help you find outliers. So you have what you do is the upper fence and lower fence, right? The upper fence is the third quartile plus 1.5 times your IQR. Remember IQR, just going to jot this down here so you remember. IQR was Q3 minus Q1. So you do have to find that first. The lower fence is Q1 minus 1.5 times the IQR. So you find these fences, right? These are like imaginary numbers. These are not actual values in your data set. They're just fences that we found by using this formula. Now, once you find these fences, look at your data. If any value is above that upper fence value, it is considered an outlier. Then you look at your data, and if there's any data values lower than the lower fence value, it is considered to be a lower outlier. So instead of just kind of saying, yeah, that looks like it's an outlier, it's pretty big, or that looks like an outlier, it's kind of small, we're going to actually define them using these formulas. So we find the upper and lower fence, doing some real quick calculations. It doesn't involve too much work. And then we actually go ahead and look at our data and determine, do we have anything bigger than the upper fence? Anything smaller than the lower fence? If so, those get called outliers. All right, that's it. I'm going to have a second video for this that gives you an actual example of doing all this stuff with a set of data. I'd highly encourage you to watch that video. That way you can actually see me put all of the stuff we learned here to use.